Hello student, welcome back. It is module 5 and the last module of microcontroller and embedded system, and it is lecture 2 of module 5, Introduction to Robotics. In the last class, we have given brief history of robotics, then how the concept came, Asimov humanoid robot, then the industrial robot Puma, then different photos of how the robots can be used, different examples. For engineering design purpose, different popular robot, how they are very popular to youngsters or we people. In the games, they are used very popularly. These are the popular games used and their names. And different definition of robot. What is the definition of robot? Robotics, degree of freedom, this is how example of a robotic leg, manipulator, anthropomorphic, end effector, workspace, position, orientation, pose, link, joint. So it is a revolute R, prismatic P, universal U, and spherical S. Common robot joints are shown over there. Position, the translation, location of an object. Orientation, the rotation, angular location of an object. An airplane's orientation is measured by roll, pitch, yaw, angles. Pose, position and orientation taken together. Link, a rigid piece of material connecting joints in a robot. Joint, the device which allow relative motion between two links in a robot. Kinematics, the study of motion without regard to forces and torques. Dynamics, the study of motion with regard to forces and torques. Actuator provides force and torque for robot motion. Sensor reads actual variables in robot motion for use in control. Haptics, from the Greek meaning to touch. Haptic interfaces give human operators the senses of touch and forces from the computer either in virtual or real remote environments. Also called force reflection in telerobotics. Application. Traditionally, robots are applied anywhere one of the 3Ds exists, in any job which is too dirty, dangerous and or dull for a human to perform. Industry. Industrial robots are used in manufacturing, pick and place, assembly, welding, spray painting, deblurring, machining, etc. Remove operation. Remote application for robotics include undersea nuclear environment, bomb disposal, law enforcement, and outer space. These are the examples. Services. Service robots have been employed as hospital helpmates, handicapped assistants, retail, household servants, vacuum cleaner, and lawn movers. Common robot design. Translational arm designs. Cartesian robot. Cartesian robot have three axes of movement x, y, z. They are constructed of three mutually orthogonal P joints. With variable lengths L1, L2, L3, used for pick and place tasks and to move heavy loads, also called Granty robots. They can trace rectangular volumes in 3D space. Cylindrical robot. Cylindrical robot positions are controlled by a variable height L1 and an angle theta 2 and a variable radius L3. P joint, R joint, and P joint. These robots are commonly used in assembly tasks and can trace concentric cylinders in 3D space. Spherical robot. Spherical robot have two orthogonal rotational r-axes with variables theta 1 and theta 2 and one P joint. Variable radius L3. The robot's end effectors can trace concentric spheres in 3D space. These are the examples. SCARA, Selective Compilance Articulate Robot Arm, Robot. SCARA robots have two R joints theta 1 and theta 2 plus a P joint D3 perpendicular to that plane of motion to achieve a 3D XYZ workspace. R joint angle theta 4 is the single rotation SCARA robot wrist. These are common tabletop assembly robots. The figure shows actuated robot. Articulated robotic assembly, the human arm in their 3D motion, they are anthropomorphic. They have three R joints with three variable angles theta 1, theta 2, theta 3, respectively the human body wrist. One DOF shoulder and elbow joints. They are versatile robots but have more difficult kinematics and dynamics control equation than other serial robots. All of these robots architectures may be used with a variety of robot wrists to provide the orientation of DOF. A wrist pitch with variable angle theta 4 is also shown with the articulated robot below. The example showing theta 1, theta 2, theta 3 movement and corresponding actual figure showing it is a welding operation it is carrying on. Orientational wrist designs. The standard robot design presented in the previous subsection focus on the primary XYZ translational motion for manipulators. Exception, the scenario SCARA robot is shown including its single wrist roll joint theta 2. The current subsection presents some common robot wrist design to provide primary orientational motion of the robot end effort. These are mounted on the end of the three DOF translational robot arms to form serial robot with translation and rotationally capability. Note primary above because the three translational joints also cause rotational and also the three wrist joint can cause translation of the tool. If the robot wrist design is spherical, that is true, with three joint axes interacting in a single point, the translational and rotational motion of the robot may be decoupled for simpler kinematics, equation and control. So SCARA 1 DOF roll wrist, Mitsubishi 2 DOF pitch roll wrist and corresponding diagram. Offset 2 DOF pitch yaw wrist for axis metric task. Puma 3 DOF roll pitch roll wrist. These are different examples. Fans S10 offset 3 DOF roll pitch roll wrist. FTS offset 3 DOF pitch yaw roll wrist, human 3 DOF yaw pure roll wrist, 3 DOF Rashim singularity free pitch yaw roll Omni wrist. The Roshium Omni Wrist has a singularity-free 3 DOF pitch yaw roll design. In this case, the rotation all occur independently. That is the pitch yaw roll order is arbitrary. There are singularities with this wrist design, but they are designed to lie in the forearm outside of the joint limits. The Omni wrist has a large rotational workspace with both pitch and yaw axis rotation plus minus 90 degree independently, and the roll axis with a huge plus minus 360 degree capability. The Omni wrist can also be equipped with an additional unlimited bidirectional roll motion for actuating rotating tools within the existing wrist. VGT 3 DOF roll pitch yaw parallel wrist, OU 3 DOF roll pitch yaw parallel wrist, AAI arm 2 4 DOF roll yaw pitch roll wrist. Mobile robots. Mobile robots have wheel, legs, or other means to navigate around the workspace under control. Mobile robots are applied as hospital helpmates, vacuum cleaners, lawn movers, along other mobilities. These robots are good sensors to see the workspace, avoid collision, and get the job done. The following 6 images show Ohio University involvement with mobile robots playing soccer in the International RoboCup competition. Early conceptual design, RoboCup playing field, player and one goalie. So it is RoboCup player CAD model, RoboCup player hardware, RoboCup goalie CAD model, RoboCup goalie hardware, lawn mover robot, vacuum cleaner robot. Human robots. Many young students expect to see C3PO from Star Wars walking around when visiting a robot laboratory. Often they are disappointed to learn that the state of the art in robotics still largely focuses on robotic arm. There is much current research work aimed at creating human like robots that can walk, talk, think, see, touch, etc. Generally, Hollywood and science fiction led real technology by at least 20 or 30 years. This is NASA JSC Robonaut, Honda humanoid robot. This is Darwin Op 20R 20 DOF humanoid robot, mobile walking soccer robot. Height 455 millimeter, about 18 inches, mass 2.8 kg, just over 6 pound weight, 2 DOF pan tilt head, 2 3 DOF arm and 2 6 DOF legs. Astronomers and self-contained onboard sensor, face down and back down recovery modes. Now parallel robots. Most of the robots discussed so far are serial robot arm, where joints and links are constructed in serial fashion from the base, with one path leading out to the end efforter. In contrast, parallel robots have many arms with active and passive joints and links, supporting the load in parallel. Parallel robots can handle higher loads with greater accuracy and higher speeds and lighter robot weights. However, a major drawback is that the workspace of parallel robot is severely restricted compared to equivalent serial robots. Parallel robots are used in expensive flight simulators as mechanical machining tools and can be used for high accuracy, high receptibility, high precision robotic surgery. Steward platform parallel robot, and in the right side parallel platform robot at Ohio University. Delta 3 DOF translational parallel robot. Cable suspended robot picture below are a special kind of parallel robot where lightweight stiff strong cables are both the actuator and structure for the robot. Though a disadvantage is you cannot push on a cable, you cannot apply only tension. Cable suspended robots have large, even huge translational workspace, unlike most parallel robots. 6 DOF NIST RoboCrane. 7 DOF cable suspended robot, deployable scratch, search and rescue cable robot. Now the scenario comes soft robots. Soft robots are constructed from high compliant materials. Often they are developed from a high degree of biomimicry, such as for octopi and elephant trunks. Their absolute rigidity and accuracy are very low when compared to traditional rigid robot. However, their safety is inherently very good, including the ability to work among humans and evolve objects for grasping them. Often they are actuated by air or other fluid, pressure and or artificial muscles, which are generally much more difficult to control than those of traditional robots. In the above figure, it is showing octopus inspired soft robot Quadrupus, and below it is elephant trunk inspired from soft robots. In a twist on history where Hollywood often leads technology by decades, the soft robo Bimax in the film Big Hero 6 was strongly inspired by the work in CMU Soft Robots Lab. Soft robot Baymax from Big Hero 6. The Venn diagram below relates hard versus soft, discrete versus continuous, and non redundant versus redundant versus hyper redundant kinematic redundancy robots. Then the ensuing table presents characteristic properties, capabilities, and design of rigid versus discrete, hyper redundant versus hard continuous versus soft robots. These are showing hard versus soft robot Venn diagram. So, properties of DF, degree of freedom, actuators, these are the different properties: material strength, materials, capabilities, accuracy, load capability, safety, dexterity, working environment, then manipulatable objects, comfortability of obstacles, design, controllability, path planning, position sensing, inspiration. For rigid robot, corresponding few, then few discrete, then metal, plastic, and these are the tables showing how they are contrast between the different categories. While in case of rigid, degree of freedom is few. In case of discrete, hyper-redundant, degree of freedom is large. Hard continuous, degree of freedom is infinite. Where it is soft, also infinite. So this table showing how they are working and how their degree of freedom and how it can be used. Like actuators, for rigid robot, it is few and discrete. For discrete hyper-redundant, it is many and discrete. For hard continuous, it is continuous, and for soft, it is continuous. Material strain, none, none, and hard continuous, it is small, and for soft, it is large. Material for rigid robot, it is metals or plastic. For discrete hyper-redundant, it is metal and plastic. For hard continuum, it is sharp memory alloy, and soft, it is rubber or electrolytic. And this table shows how they can be used. For design purpose, for rigid, it is easy to design. The second one is medium to design. Third one is difficult to design. And the fourth one is also very difficult to design. Now, from the point of view of path planning, rigid is very easy for path planning. The second one is harder. Third one is difficult. Fourth one is also difficult. So, we are ending today's session over there, and for references, these are the references, and thank you. We are ending today.